Mars, our celestial neighbor, has captivated humanity for centuries. Its reddish hue, visible even to the naked eye, sparks our curiosity and fuels our imagination. We've sent rovers to explore its surface, uncovering evidence of ancient rivers and oceans. These tantalizing clues suggest a planet that might have once harbored life. Today, Mars is a frigid desert, its thin atmosphere offering little protection from the harshness of space. Temperatures plummet far below freezing, and liquid water is scarce. Yet beneath this desolate facade lies the potential for transformation. Scientists believe that by warming Mars we could unlock its hidden potential and pave the way for human exploration and settlement. This ambition is not driven by mere scientific curiosity, though that plays a part. It stems from a deeper yearning to extend humanity's reach beyond Earth, to find new homes among the stars and ensure the survival of our species. Mars, with its potential for harboring life, represents a beacon of hope in this cosmic quest. Imagine a future where humans walk on Mars, not just as explorers, but as inhabitants. Picture bustling Martian cities, enclosed ecosystems teeming with life, and vast fields of crops stretching across the once barren landscape. This is the dream that drives us to explore the possibility of warming Mars. Before we delve into the how of warming Mars, let's understand the why. Mars, as it stands, presents a formidable challenge to human life. Its atmosphere, composed primarily of carbon dioxide with a smattering of other gases, is about 100 times thinner than Earth's. This thin atmosphere provides little insulation, resulting in extreme temperature swings. Daytime temperatures at the equator can reach a balmy 70 degrees Fahrenheit, but at night, they plummet to 200 degrees below zero. This extreme temperature variation makes it impossible for liquid water to exist on the surface for extended periods. Water, the elixir of life as we know it, is locked away as ice beneath the surface or as vapor in the thin atmosphere. Adding to the challenges is the lack of a global magnetic field. Earth's magnetic field acts as a shield, deflecting harmful radiation from the sun. Mars, lacking this protective barrier, is bombarded by radiation that would be lethal to humans. This radiation also strips away the Martian atmosphere, making it even thinner over time. These harsh conditions make it clear that transforming Mars into a habitable planet is no small feat. It requires a fundamental shift in its climate and environment. This is where the ingenuity of scientists comes into play, exploring innovative solutions like engineered nanoparticles to tip the scales in favor of life. Central to the vision of a habitable Mars is the creation of a breathable atmosphere. Currently, the Martian atmosphere is far too thin and lacks sufficient oxygen to support human life. We need to find a way to thicken the atmosphere and increase its oxygen content. One proposed method involves releasing trapped greenhouse gases already present on Mars. These gases, such as carbon dioxide and water vapor, are found in frozen form beneath the surface and in the polar ice caps. By introducing heat, we could potentially vaporize these gases, thickening the atmosphere and triggering a greenhouse effect. A thicker atmosphere would trap more heat from the sun, leading to a gradual warming of the planet. This warming in turn could melt more ice, releasing more greenhouse gases and further amplifying the effect. This self-sustaining cycle, if successful, could eventually lead to a warmer Mars with a denser atmosphere. However, even with a thicker atmosphere, the challenge of generating breathable oxygen remains. This is where innovative solutions like engineered microorganisms or artificial photosynthesis come into play. These technologies, still in their infancy, hold the potential to convert Martian carbon dioxide into breathable oxygen, paving the way for a truly habitable planet.
In the realm of nanotechnology, scientists are exploring the use of engineered nanoparticles, minuscule particles with unique properties that can be tailored for specific tasks. These nanoparticles, often thousands of times smaller than the width of a human hair, hold immense potential in various fields, including medicine, electronics, and even planetary engineering.
Engineered nanoparticles can be designed to absorb specific wavelengths of light, making them incredibly efficient at trapping heat. Imagine spreading a thin layer of these nanoparticles across the Martian surface. These nanoheaters would absorb sunlight and radiate heat, warming the surrounding environment.
Furthermore, nanoparticles can be engineered to interact with specific molecules such as carbon dioxide. By designing nanoparticles that bind to carbon dioxide, we could potentially sequester this greenhouse gas from the atmosphere, mitigating its warming effect and controlling the pace of climate change on Mars.
The ability to tailor the properties of nanoparticles makes them versatile tools for planetary engineering. By carefully selecting their size, shape, and composition, scientists can fine-tune their behavior and optimize their impact on the Martian environment.
Imagine a future mission to Mars, not with bulky equipment and heavy machinery, but with a payload of engineered nanoparticles. These microscopic particles, light enough to be carried on a spacecraft, could be deployed strategically across the Martian surface.
One proposed method involves dispersing nanoparticles as a fine dust over select areas, such as the polar ice caps or regions with high concentrations of frozen carbon dioxide. These nanoparticles, acting as miniature solar panels, would absorb sunlight and convert it into heat, gradually warming the surrounding environment.
As the ice and frozen carbon dioxide begin to melt and vaporize, they would release greenhouse gases into the atmosphere, thickening it and further enhancing the warming effect. This process, known as the solid-state greenhouse effect, could trigger a cascade of positive feedback loops, leading to a gradual warming of the planet.
Another approach involves using nanoparticles to darken the surface of Mars. Darker surfaces absorb more sunlight than lighter ones. By spreading a layer of dark nanoparticles, we could increase the amount of solar radiation absorbed by the planet, leading to a gradual increase in temperature.
While the prospect of warming Mars with engineered nanoparticles is enticing, it's crucial to acknowledge the delicate balance we must strike. We're not simply flipping a switch to turn up the heat, we're attempting to orchestrate a controlled and gradual transformation of a planet's climate.
One of the primary challenges lies in managing the pace of warming. Too rapid a change could have catastrophic consequences, leading to unpredictable weather patterns, massive dust storms, and even the loss of precious water resources to space. It's a delicate dance between pushing the planet towards habitability without tipping it into chaos.
This is where the precision offered by nanotechnology becomes crucial. By carefully selecting the types of nanoparticles used, their concentration, and their distribution, scientists can fine-tune their impact on the Martian environment. This level of control is essential for avoiding unintended consequences and ensuring a smooth transition towards a more habitable planet.
The key lies in continuous monitoring and adjustments along the way. We need to constantly assess the planet's response to our interventions and be prepared to adapt our strategies accordingly. This iterative approach, guided by scientific data and a deep understanding of planetary systems, is paramount to the success of any terraforming endeavor.
As with any ambitious endeavor, the prospect of warming Mars using engineered nanoparticles is not without its risks. While the potential benefits are immense, it's crucial to acknowledge the possibility of unintended consequences. We're venturing into uncharted territory, and caution must be our guiding principle.
One concern is the potential for ecological disruption. Mars, while seemingly barren, might harbour microbial life forms that have adapted to the planet's harsh conditions. Introducing foreign elements like nanoparticles could disrupt these ecosystems, potentially leading to unforeseen and irreversible consequences.
There's also the risk of triggering runaway effects. We're dealing with complex systems, and our understanding of planetary climates, while constantly evolving, is still incomplete. It's possible that our interventions could trigger feedback loops that spiral out of control, leading to extreme climate changes that render the planet even less hospitable.
Furthermore, the long-term effects of engineered nanoparticles on the Martian environment remain uncertain. Will they degrade over time? What happens to the byproducts of their degradation? These are questions that require thorough investigation before we embark on large-scale planetary engineering projects.